Hello, my name is Ethan Lego, and this is my third project for my fluid mechanics course. As you can see here, I've already set up the viscous laminar, turbulent, and inviscid flows, but I'm going to walk through how to do each of them. In this video, I'm just going to be focusing on laminar, and additionally, for the following videos, the geometry is going to be the exact same. There shouldn't be any changes to those. And the meshes should be pretty similar. I believe there's a change for Invisid, but that's it. So I'm just going to start by creating a new system. I'm going to be calling it video example laminar. And I'm going to go into geometry and create a new geometry. All right, so now that I'm in Design Modeler, I'm going to I'm going to go to settings actually. I'm going to turn the grid on. I'm going to make major grid spacing 10 and minor grids is going to stay at 5. It just makes it easier to visualize everything. So I'm going to go to draw and select circle and just draw that out. Same thing with rectangle. Make arbitrary circles and rectangles. And then I'm going to dimension them. I'm going to take diameter. I'm going to do horizontal and vertical. So now I'm going to dimension them. Our circle, the cylinder wall should be 1 meter, given the project description. For our simulation area, I'm going to choose 50 meters by 50 meters, just so that we have a good, simulation area without it causing any boundary layers or anything that'll affect the cylinder. And so you can see that it's very off center from the circle. So in order to fix that, I'm just going to go and dimension from the axis for both of these lines and make sure they're both 25 to center them. And so now we have a very good area for all of our velocity contours, streamlines, vectors, all of that sort of thing. So now I'm going to go to Concept, Surface from Sketch. Going to select Box select all of our lines, and hit Generate. And so now we have our surface that we're going to work on. And I believe that's it for Design Modeler. Okay, so now I'm going to start the mesh. Click Edit. All right, so now that we're loaded in, I'm just going to name all of my edges. So the top and bottom are going to be just sim. Um, my left side is going to be my velocity inlets. The right side, pressure outlets. And the circle in the center is it's actually a cylinder, but we're looking at it in 2D, so we're going to call it cylinder wall. All right. So now I'm just going to go to mesh, method. I'll select the face and we'll be using triangles. Click generate. That was pretty fast. However, it's not a very good mesh, so we're gonna insert sizing. I'm going to select circle. We're gonna select a number of divisions of 500. And we'll make sure that our behavior is hard. and click generate. All right, so we've created that now, but we're going to add inflation. Select the face, and for our boundary, we're going to select that circle again. And we're going to select first layer thickness. And for this one, I'm going to do 1 meter. And the maximum layers is going to be 150. And that should be it. Click generate. All right, so that inflation has been finished. So you can see well more defined mesh around the circle where the majority of our what we're interested in is. But you can still see that the rest of it is kind of it's not very um, accurate, not very defined. So we're gonna make sure that our element size outside of that is 0.6, and that's gonna reduce it a little. All right, now that that's generated, you can see now it's a lot more defined, a lot smaller element sizes, which will give a more accurate answer. So that's it for mesh, and I'm going to move on to setup. I'm going to click edit, double precision, and I'm going to do 4 processors. Okay, so now that our mesh has loaded in, I'm just going to make sure that we're pressure based. For time, we have steady time, and we're using 2D planar. For our model, we're going to be changing it to laminar. Yep, that looks right. And for our material, we are going to use air, but I'm just going to make sure that they are the right density and viscosity. Yep, that looks correct. Save that. I'm just going to double check that it's going to be using air instead of any other fluid or solid material. Yep, air, okay. And so now for our boundary conditions, for our velocity inlet, I'm going to use a velocity of 0.5 meters per second. And with this velocity and the properties for air that I'm using, I'm going to get a Riddle's number of approximately 35,000, which is well below the 500,000 critical number. I'm going to hit apply there. I'm going to make sure that my pressure outlet looks correct. Yep. And that our cylinder wall um, is no slip and also um, the stationary. Yeah. Okay. Cool. I'm going to go to reference values, compute from, making sure to compute from the velocity inlet, and all of our values look correct. Selecting the surface body, and yep, and methods. I'm just going to make sure got our method correct. Least squares, second order. Okay, perfect. In report definitions, I'm going to create a new force report for drag. I'm going to select drag coefficient. I'm going to call it drag coefficient as well. And selecting cylinder wall. And clicking OK. Closing that. For our initialization, I'm going to change the Number of iterations 30 just to be extra cautious. And for our calculations, I'm going to use 500 iterations. You couldn't go up to 1,000, but that just, you know, 500 is safe enough. So I'm going to click calculate. Okay, so it looks like our calculation is complete. I'm just going to go to the drag coefficient and make sure that it looks correct and get this smaller. Okay. Yep, so a drag coefficient of 0.75 works roughly um, for this application. Um, and so then I'm also going to go to plots, XY plot. You know, I'm making two plots. The first one is going to be my pressure coefficient. So under pressure, I'm going to do pressure coefficient, and it's going to be across the cylinder wall. And so as you can see, it follows like roughly the curve that it should, based off of the theoretical pressure coefficients around a cylindrical wall. And then my second plot is going to be a velocity across the cylinder. So velocity wall, it's like velocity magnitude around the cylinder, um, and create. And this should be 0. Um, this also aligns with the theoretical. Um, yep, so that's it for the solver. So now I'm going to go to results. Okay, so now that I'm in CFD post, I'm going to create two different contours. My first one is going to be a pressure contour, making sure to select symmetry 1, pressure, and I'm going to be doing 100 contours. Okay, so if you zoom in, you can see that you know, there's a pressure spike in the front, and you know, pressure drops in the rear. Um, I'm going to do a second contour of velocity. And this should once again be symmetry 1, making sure to select velocity U and 100 contours. All right, so you can see that for the most part, it's very laminar. Um, if we had a more viscous fluid, it would more closely follow the outline on the um, downstream side of the circle. But for air and the Reynolds number that we needed, this is just how it came out in the simulation. Um, yeah, and so finally, I'm just gonna go to my legend, make it horizontal, make it a little bit larger, and select fixed. And so um, this is these are the visuals that will be in my my project's document. One more thing, I'm going to also do streamlines for velocity. I'm going to select start from velocity inlet, making sure they're equally spaced, and I do 5,000 points just so that it's, you know, more defined. Okay, so and here are those streamlines, very similar to the velocity contours. So yeah, there we go.